Okay, so I want to go over the exit card slash entrance card that went over days 1 through 4 for Chapter 6. That will be covered on Monday's quiz. So question 1 said to answer the following based on this function f of x. First thing I'm asked to do is state the roots. So if I look at my factored function, I can see that my first root is going to come from the factor x, so x is equal to 0. Second root comes from the factor x plus 4. So that's going to give me a root of x equals negative 4. Then I look at the factor x minus 2. That's going to give me a root of positive 2. And the factor of x plus 1 is going to give me a root of negative 1. Then it asks me to state the multiplicity of each root, and that's going to be based on what exponent that factor is raised to. So for the factor of x, it's raised to the first power, so x equaling 0 has a multiplicity of 1. Same thing with the factor x plus 4. This will have a multiplicity of 1. X minus 2, that factor, that root of 2, is being raised to the third power. So this multiplicity is going to give me a multiplicity of 3. And the last factor, x plus 1, that root of negative 1, has a multiplicity of 2. Let's just review what multiplicity really tells us. If the multiplicity is odd, that tells me that my graph is going to cross the x-axis at that root. So where the multiplicities are 1, 1, and 3, the graph will cross the x-axis. Where my root of negative 1 has a multiplicity of 2, that means my graph will be tangent to the x-axis at that root. Now if we want to talk about the degree of the function, one way to do this is to take the multiplicities and add them up. So I have a multiplicity of 1 plus 1 plus 3 plus 2, which would give me a degree of 7. So this is a 7th degree polynomial. Okay, and that also tells me that the degree here is odd. So I'm going to also note odd degree. The other way to find the degree would be to write this function in standard form, which would require you to multiply out every factor and rewrite it in standard form in descending order with your exponents, which would take a lot of time. So taking the multiplicities and adding them up is definitely the preferred way to find the degree. Then it's asking us to state the sign of the leading coefficient. So if I take a look at the front of this function, there is a negative 1 in front of x, so the leading coefficient is negative. And now that I know the degree and the sign of the leading coefficient, I am able to state my end behavior. So this is an odd degree function with a negative leading coefficient. So my end behavior is going to go up on the left and down on the right. So the formal way to write that is to say, as x approaches positive infinity, my f of x, or y's, are going to approach negative infinity. Usually, if I take a positive number and raise it to an odd power, it would stay positive. But because of this negative leading coefficient, my y's are going to become negative. So the same will be true in the reverse. As I take x and it approaches negative infinity, f of x is going to approach positive infinity. Normally, if I took a negative number and raised it to an odd power, I would get a negative y. But there's a negative in front, that leading coefficient, which would turn that negative into a positive. Now we're asked to state whether the function is even, odd, or neither. I'm actually going to leave this question. I'm going to go sketch it, and then we'll have a better idea of how to answer that part. Okay, so if we go to sketch this function, the first thing I like to do is think about my end behavior. We said that it's going to go up on the left, down on the right. So I like to give myself a little arrow down here in the fourth quadrant to show that the right side of my graph will go down, and an arrow up here in quadrant 2 to show that the left side of my graph will go up. I'm also going to plot my zeros. So I have a 0 at negative 4. I have a 0 at negative 1. I have a 0 at 0. And I have a 0 at positive 2. Then I also want to remember where the crosses and the tangent aspects are of my roots. So at negative 4, I am crossing the x-axis. So I'm going to take my end behavior here and cross through at negative 4. Then I know that I'm tangent at -1 because that was my factor that was raised to the second power with an even multiplicity. So I need to have some turning point to get me back to my root of -1. Then I'm going to bounce off this root of -1. Then I do need to cross through at 0, so there must be some other turning point that will bring me through across at 0, and then another turning point that will bring me through to cross at 2. And again, my end behavior was over here. Not the prettiest of graphs, but it gets the job done. I crossed at -4, 0, and 2, and I was tangent at -1. And my end behavior is indeed up, down. Okay, so now that we have our graph, our function graph below, we can kind of answer this question, second to last question, a little bit better. We want to know whether the function is even, odd, or neither. So let's just remember, even means that my graph is symmetric to the y-axis, meaning every xy ordered pair would then have a -x, y match. And then for odd functions, we have symmetry to the origin. Which again, I want to represent that using ordered pairs. I'm going to take both x and y and negate them from my original ordered pair, and that will both be on my graph. If I don't see this symmetry to the y-axis or this symmetry to the origin, then it just means that this is a function that doesn't have an even or odd nature to it. So if I just look at this graph, if I wanted to go and take a look, it does not have symmetry to the y-axis. The end behavior is in opposite direction, so it's absolutely not an even function. And then if I try to look at this graph, and I want to determine if it's symmetric to the origin, I'm going to show you one way to do that is to flip it over. Okay, so to show this, I just kind of clone my graph here. So if I take this sketch, I just have two of the same sketch here, and I make a rotation of 180 degrees, if they looked the same, then I would know that there's symmetry to the origin, but we can tell right now that these graphs do not appear to be the same with symmetry to the origin. Every xy ordered pair is not mapping to another -x, -y ordered pair on the graph. So this function is also not odd, so it would be neither. The other way that we can determine whether this function is even or odd a little bit quicker than just looking at the graph is to type the equation into your y equals, go to your table, so second graph, and look at these y values. We know that for an even function, right, every xy on a graph should also have a -x, y, because there's symmetry to the y-axis. And for odd functions, xy should then also have -x, -y. So if I look at, let's just say, +1. +1 is associated to +20. So if this was even, -1 should also be associated to +20, and it is not. If this is odd, -1 should then be associated to -20, which it also is not. So if you analyze these xy ordered pairs, you're going to notice that they do not share an even or odd relationship. And for question number 2, we're given a graph and asked to answer 2 questions about it. The first one is saying, is there an absolute max, min, or neither? So looking at this graph, I can see that there is an absolute maximum. It is the highest point on the graph. But because my end behavior goes down to -infinity, there would not be an absolute minimum. So there is an absolute maximum on this graph. And just to review, this turning point would be a relative minimum. This turning point would be a relative maximum, but there is no absolute minimum. Now we're asked to write a possible equation for this. So I first want to identify my roots. So here, off to the left, I can see that I have a root of -2 in factored form. That would be x plus 2. And because this is a turning point, again, I can see that on either side of this root, the graph is below the x-axis. It bounces off the x-axis and it's tangent. So that we're going to say is an even multiplicity. We're going to say it's raised to the second power. I have another root here of positive 1. So x equaling 1 in factored form would be x minus 1, and that is crossing through the x-axis, so that's going to have a multiplicity of 1. And then my last root here is x equals positive 3, which would be in factored form x minus 3, and again this is crossing through the x-axis, so that would also have a multiplicity of 1. Now, based on the fact that I can see the end behavior is pointing down, down, I know that the leading coefficient here should be negative. And now I have enough information to write my functions equation. So, f of x is going to be equal to negative. My first factor from left to right is x equals 2 squared times x minus 1 to the first times x minus 3 to the first. And again, these are factors, meaning they are multiplying each other, so the commutative property does apply. If you wrote your factors in a different order, as long as they are to the same multiplicity and the negative is in front, that would be equivalent.